Welcome to the video lecture on summation notation and area. Let's start by talking about summation notation. Now the sum of n terms, a sub 1, a sub 2, a sub 3, all the way up to a sub n, is written a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. This would be the long way to write it. What we can do to avoid writing all of that out is use something called summation notation, which is this expression over here. You see the Greek letter sigma, that's a capital S, and underneath it we have an index. This is called the index of summation, that's that little I, and it tells you how you want I to vary. We want I to start at 1 and go up till n, and we're going to be plugging that I into this part of the formula right here. So when I is 1, we get a sub 1. When I is 2, we get a sub 2. And when I is n, we get a sub n. And what are we going to do with all of those terms? Well, that's what the sigma means. It means to add. It means to find the sum. So I is called the index of summation. A sub I is the ith term of the sum. And the upper and lower bounds would be this 1 and this n. So let's practice using this summation notation. So if I wanted the sum as I varies from 3 to 6 of I squared, we're going to start by letting our very first I be 3, that's this lower bound, and we're plugging it into this formula, I squared. So that would become 3 squared. If I was 4, then when I plug that into my formula, I get 4 squared. When I is 5, I would get 5 squared. And when I is 6, I would get 6 squared. And the summation notation means sum up those answers. So we're going to add together all 4 of these. So this would be 9 plus 16 plus 25 plus 36, which is 86. Okay? So if you look at the next example, it looks very similar. The only difference is I've changed out the letter. Instead of using I, now I'm using K. So I've changed out that variable. We still want K to start at 3, and we're using this formula. So when I plug in 3, this is going to give me 3 squared still. When K is 4, we get 4 squared. When K is 5, we get 5 squared. When K is 6, we get 6 squared. And we're summing up all 4 of those. So even though I swapped out my variable name, I still get exactly the same sum because I had exactly the same formula and I had the same lower and upper bounds. Typically in summation notations, your index of summation is either I, J, or K. Those are the typical variables that you see. Now on the next example, there's a couple of different variables going on here. We want K to range from 1 up to n. Now in this formula, the K, which is right here, is the only thing you're plugging in for. So we're going to start by letting K be 1. So this n out front stays n, and then this K becomes a 1 plus a 1. If K was 2, then we still have that n out front, but now we're going to get 2 plus 1 in the parentheses. If K is 3, then this would be n times 3 plus 1. And we're going to do this all the way until K becomes an n. So you'll still have that n out front, but then this K right here becomes n plus 1. And now we're going to add all of these together. So this one is a 2 times an n, plus a 3 times an n, plus a 4 times an n, plus n times n plus 1. Okay? And you can't really simplify that so much because we don't know what n is. So you could just leave it like that. All right, now the next example is one we're actually going to see quite a bit today in this lecture. This is f of x sub I times delta x, and we're letting I vary from 1 to n. So the only place in this formula where we see the I is right here, and that's called a subscript. So all we're going to be changing is that subscript on that x. So when I is 1, this is f of x sub 1 times delta x. When I is 2, this is f of x sub 2 times delta x. Plus, when I is 3, f of x sub 3 delta x, and so on, all the way up till I becomes n, so this will be f of x sub n times delta x. Okay, so there's our answer. We're just going to leave it like that. So in number 5 here, we're going to go in reverse. So this time I'm actually giving you kind of like this right-hand side, and I'm asking you to figure out what would be the summation notation that it came from. So the trick to doing these is figuring out what is changing in the formula. What number or position is changing, and that's going to be where you put your I in your formula. So you want to compare, for example, this whole term to this whole term and to this whole term. What's different about them? The only thing that's changing is this 2 and this n, and even though there isn't one here, you can think of this as having a times 1 right there, an implied multiplication by 1. So that 2 over n is getting multiplied by something that's changing on the top, and that is where your I is going to go. So our formula is going to look exactly like one of these expressions, 1 minus parentheses. Where that little circle is, which is the top where this 2 is, that's where you're going to put your I. So 2 times I over n minus 1 quantity squared times 2 over n in parentheses. So all I did was I changed this to an I, changed this to an I, changed this to an I. And then, now that we know what our formula needs to look like, how does I vary? What was the very first I that this one used? It used 1, then it went to 2, and it stopped at n. So we want this sum to stop at n. So that is your summation notation. And that's it. Let's try another one. Write in summation notation the sum of all of these. So again, look for where the numbers are changing, and that's going to be where you put your I. So when I look at this, this is a 1, then a 2, and then it ends at a 4. So that's where your I needs to go. So the formula should look like 1 minus I over 4 quantity squared. And then for my bounds, what was the first I that was used here? 1. So that's your lower bound. And what was the last I that was used? 4. So that's your upper bound. And there's your answer. Now there are several formulas that have summation formulas to them, and we're going to sort of compute a couple of them, and then I'll just give you the formulas for 2 more of these that you'll want to have memorized to be able to use in the problems that you'll see in this lecture. So this first summation formula says, what is the sum of a constant c as I goes from 1 to n? So let's write out what this would look like. So when I is 1, your formula is just c. And notice there's no I in there because this is a constant. So it doesn't matter what number your I is, you're always going to get c back again. So when I is 2, you'll get c. When I is 3, you'll get c, all the way up until when I is n, and you'll still get c. And what are we doing with these? We're adding them together. So how many of these c's are there? Well, there's going to be n of them because we have n i's. So what do you get when you add c to itself n times? Well, that's just n times c. So here's our formula. The sum of a constant from 1 to n is just that constant times n. Okay? All right, let's try the next one. This is the sum as I goes from 1 to n of I. So this time there is an I in my formula. So when I is 1, we're just going to get 1. When I is 2, we get back I, which is 2. When I is 3, we get back I, which is now 3, all the way up until when I is n, we're going to get back n, and we're adding these together. So this is just the sum of the integers from 1 to n. So I'm going to give you a formula for this. We're actually going to derive it, and we're going to derive it. I'll do my derivation over here on the side in a slightly different kind of a proof. So the sum of I from 1 to n is 1 plus 2 plus 3 all the way up to n. Now think about that sum from 1 to n of I in a different way. It would also be the same as going and adding all of these numbers, but starting at the top and going down. So n plus the next number lower plus the next number lower all the way down to 3, 2, and 1. Okay, so in other words, here I'm adding from 1 to n, here I'm adding from n down to 1. So I'm just adding in a different order, and that's allowed because addition is commutative. So what happens if I add these two things together? Well, 1 plus n is an n plus 1. 2 plus n minus 1 is also n plus 1. 3 plus n minus 2, well 3 minus 2 is 1, so that's also an n plus 1. And the very last one here, n plus 1 as well. So each time you add down, the very first with the last, the second with the second to last, the third with the third to last, and so forth, you're always going to be getting a sum of n plus 1. And when we do this, the sum of I plus the sum of I is 2 of the sum of I. Now, how many of these are there? Well, we have n numbers going across, so there's n of these. So n plus 1 times its, or added to itself n times, is n times n plus 1. But that's twice the sum that we were looking for. We didn't want to know what the sum of I plus the sum of I was. We just wanted one of those sums. So all we have to do to finish this off is divide by 2. So the sum of I from 1 to n has as its formula n times n plus 1 over 2. So here's your formula that you want to memorize. The sum from 1 to n of I is n times n plus 1 over 2. So for example, if I asked you to add up all the numbers from 1 to 100, then that would just be 100, because that's your n, times 100 plus 1 all over 2. So that's 100 times 101 over 2, and that's 5,050. So it gives you a quick way to figure out what that sum is without having to physically add every single number from 1 to 100. You could do it, but it would take you a long time. Okay? So here's our sum formula for the sum of the integers from 1 to n. Now the rest of these formulas that I'm going to give you, they can also be proven. We're not going to spend time doing it right now. I'm just going to tell you what these formulas are. So this is the sum of the squares, and this is the sum of the cubes from 1 to n. So the formula for the sum of the squares, so this would be like 1 squared plus 2 squared plus 3 squared all the way up to n squared, has as its formula n times n plus 1 times 2n plus 1 all over 6. And the sum of the cubes, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to n cubed. You could do that, but the formula that I'm going to give you is a shortcut to get that answer right away without actually having to physically add each of those cubes. So here's the formula for the sum of the cubes, n squared times n plus 1 squared all over 4. So these four formulas, here, here, that first one we did, and this one, we're going to use these quite a bit today in our lecture. So it's recommended that you kind of memorize these four formulas only. Okay? All right, let's look at a couple of properties of these summations. Let's take a look at what happens if you have a constant k times a sub I, and you want the sum of a constant k times each of these a sub i's. Well, it makes sense, hopefully, that you can just pull that constant out and add up all the terms and then multiply that answer by your constant. Okay, so we're allowed to pull constants out, and it also should kind of be common sense that if you wanted the sum of a sub I plus b sub I, or the sum of a sub I minus b sub I, you could just take the sum of the a sub i's and either add or subtract the sum of the b sub i's. So you find each of these two sums individually and then add or subtract the answers. Okay, so let's practice putting some of these formulas into play. So this one, the sum from 1 to 15 of 2i minus 3. Now the long way to do this would be to plug in 1, then plug in 2, then plug in 3, then plug in 4, all the way up to 15. Figure out what all of those are, and then add all that up. So here's the shortcut, and that's going to be using these new summation formulas that we just figured out. Now first of all, this is a difference of two things. So I'm going to break this up into the sum of just the 2i minus the sum of just the 3. Then using that constant multiplier property that we just talked about, I can pull this 2 out. Just like that. And now what I'm going to use are the formulas. This is going back to our previous page. That 3 is a constant, so the sum of 3 is just going to be that 3 times whatever our n was, which was that 15. And then we also have the sum of I, which has as its formula n times n plus 1 over 2. And our n, again, is 15. So I'm using this formula and this formula to finish this off. So for this one, leave the 2 where it is. The sum of I is going to be that n times n plus 1 over 2. So that's the formula I'm using here, and my n is 15. So this is going to be 15 times 15 plus 1 over 2. Minus, now I'm going to use the sum of a constant rule, which is just constant times n. And here my constant is the 3, and my n is that 15. So plugging this all in, here my 2's are going to cancel. 15 times 16 is 240 minus 45, and this is 195. So there's a little bit of work involved, but it's less work than plugging in all of your different 15i values, figuring out what those are, and then adding all of that up. Okay? Let's try another one. The sum from 1 to 10 of I squared minus 1. So the first thing that I'm going to do again is separate that difference, and I'm going to make this the sum from 1 to 10 of just the I squared minus the sum from 1 to 10 of 1. Now keep in mind that we have formulas for the sum of a constant, the sum of I to the first, the sum of I squared, and the sum of I cubed. Those were all those 4 formulas we talked about on the last page. So on this particular problem, this is the sum of a constant right here. So this is just going to be that constant, which is 1, times n, which is this 10. And then this one is the sum of our squares, which we have a formula for. And the formula for that, if you look back on our previous page, is just going to be n times n plus 1 times 2n plus 1 all over 6. So on this problem, our n is 10. So this is going to be 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. So that's going to be 10 times 11 times 21 all over 6, and 1 times 10 will just be 10. And if I simplify here a little bit, this whole fraction is 385. So when I subtract 10 from that, I get 375. Okay? All right. Now we're going to manipulate these sums again, and this time we're going to add a touch of calculus to it. We're going to find a limit as this sum, the limit of this sum as n goes to infinity. So here is a summation notation formula right here, an expression. First thing we're going to do, this is a two-step problem. First thing we're going to do is we're going to use those formulas that we have for the sum of a constant, the sum of I, the sum of I squared, and the sum of I cubed. We're going to use those four formulas if we need to help us figure out what this sum turns out to be. Once we get a formula for what that sum is, we're going to take the limit of that sum as n goes to infinity. But first we're going to find out what the sum is, and it'll be a formula in terms of n, since n here is not a number, it's just an n. We don't have a 15 or a 10 to plug in. So the answer that we're going to get initially should be a formula involving n. So here's what we're going to do. The first thing we're going to do is we're going to pull out any constants that we can. Now the only thing in this formula here that's really a variable, really something that's changing, is the I. So if your expression does not have an I in it, it's considered a constant. So this 2 over n does not have an I in it, so I'm allowed to pull that out, because it's not going to be affected by that I changing from 1 to n. So get that 2 over n out of there. And now this is what we have. Now this doesn't fit any of our four formulas over here. This is too complicated. So what I'm going to need to do is break it down using some algebra. This is a quantity squared. So what I could do is I could FOIL this out. So let's FOIL it. We're going to get a 1. In the middle, we're going to get a 2i over n times 1 plus another 2i over n plus 1. So that's 4i over n. And then we're also going to get a 4i squared over n squared. That's just this term squared. Okay, now how did that help us? Well, what we're trying to do is we're trying to break this up so that I see constants, i's, I squares, or I cubes in there. And if I see those, then I'm going to be able to use the corresponding formula. Now what about these 4 over n's? They don't have i's in them, so they are going to be constants that we're eventually going to be able to pull out. So here's what I'm going to do. I'm going to leave that 2 over n where it is, and then in brackets, I'm going to break up this sum of 3 terms into 3 different summation notations. So this first one will be the sum of just 1. This second one will be the sum of 4i over n. And the third one will be the sum of 4i squared over n squared. Now this 4 over n is a constant which I can pull out of that particular sum, and this 4 over n squared is a constant which I can pull out of this particular sum. So I'm just going to do that. I'm going to pull them out, leave this guy alone for now. This becomes 4 over n times the sum from 1 to n of I, plus 4 over n squared times the sum of I squared. Now see what I've done? What I've done is I've created now here the sum of 1, which is like the sum of a constant. And I've created the sum of I, which we have a formula for, and the sum of I squared, which we have a formula for. So let's write down what those formulas are. The sum of a constant is just a constant times n. So this one's going to be c times n. The sum of I is just n times n plus 1 over 2. And the sum of the squares is that big one, n times n plus 1 times 2n plus 1 all over 6. So I'm going to substitute in those 3 formulas for these 3 boxes. It's going to get messy, but that's okay. That's what we have to do. So this becomes 2 over n bracket. The sum of 1 is going to be that constant, which is 1 times n. So this is just 1 times n. Plus 4 over n times the formula for I, which is n times n plus 1 over 2. Plus 4 over n squared times the formula for I squared, which is n times n plus 1 times 2n plus 1 all over 6. Okay? So it's getting messy, but that's okay. Keep plugging away. Now what we're going to do is try and simplify whatever we can. 1 times n is n. When I go to this factor here, the 2 cancels with the 4, giving me a 2, and couple of these n's will cancel. So I'll have a 2 times n plus 1. Over here, the 4 and the 6, I can take out a factor of 2, so I'll be left with a 2 on top and a 3 on the bottom. And one of these n's will cancel, but I'll still have 1 in the bottom. So this will be a 2 over 3n times n plus 1 over 2n plus 1. Okay? Now the next thing that I'm going to do is I'm going to go ahead and distribute my 2 across. So this will be 2n plus 2. And I'm going to go ahead and FOIL this guy out and double it all. So let's do that with a little bit of scratch work over here. So n plus 1 times 2n plus 1 is going to be 2n squared plus an n plus a 2n plus a 1. So that's 2n squared plus 3n plus 1. And then we had that 2 out front. So I now need to double that. That's going to give me 4n squared plus 6n plus 2. And that is on top all over that 3n. Last thing I'm going to do is distribute this 2 over n across to each of these terms and cancel as I go. So 2 over n times n is just 2. 2 over n times 2n, the n's cancel. 2 times 2 is 4. 2 over n times 2 is 4 over n, plus 2 over n times all of this. Nothing cancels. I can double the top, so I'm going to double all 3 of these terms. So this would be 8n squared plus 12n plus 4. And on the bottom, n times 3n is 3n squared. Now these are almost pretty much done here. What I could do is add my 2 plus my 4 to get 6. But after that, I'm pretty much done. If you really wanted to get a common denominator, you certainly could, but I recommend just stopping right here. So this is our sum formula. It will still have n in it. This is step 1. Okay? So this would be the formula that you could use to figure out what this sum is. Just plug in your n and you'll know what the answer happens to be. Now the second step of this problem is to find the limit of this as n goes to infinity. So we want the limit as n goes to infinity of this whole formula that we just came up with. Now the reason I recommend not taking this, too far is because if you think about what's going to happen in our limit here, the limit of a sum is the sum of the limits. So I can just take the limit of each piece. Now the limit of 6, the limit of a constant is a constant. So the limit of 6 will stay 6. On this one, the limit of 4 over n, if n is getting big, this is like 4 over infinity. And a number over something infinite gets small. So this is going to go to 0. And then this last one, this is like the kind of limits that we would see when we were looking for horizontal asymptotes. You have to think about what dominates on top, which would be this term, over what dominates on the bottom, which would be this term. 8n squared over 3n squared, the n squareds cancel. So this, in the limit, is going to go to 8/3. These two terms become insignificant as n gets really, really large. We only have to worry about the dominating terms. So we get 6 plus 0 plus 8/3. And now if you want to get a common denominator, 6 is the same as 18/3. So 18/3 plus 8 is 26/3. And there's the limit of our sum. Now as you can tell, these kinds of problems are not short. They take a lot of time to do, and they're kind of tedious because you have a lot of steps involved. So prepare for that. Make sure that you have enough paper, a good eraser, because these problems are kind of yucky to do. Now, why do we need to do those kinds of problems? Well, let's see what they're good for. We're going to build up to it. So on this next example, This is something that we often need to do in calculus. We need to approximate an area of a region bounded by a curve. So here we have the curve 4 minus x squared, just a nice parabola. And we want to find the area under that curve between the curve, the x-axis, and the y-axis. So we're looking for this area right here. So one way we can approximate what that area is, we can't find it exactly, at least not yet, because it's not a nice common shape. You know, if it was one big rectangle or a triangle or a circle even, we would have geometric formulas for finding the area of that particular shape. But this shape right here, because of that curvy piece that's coming down, it's not one of our known geometric formulas. So we don't have a formula that we can plug in for it. So what we're going to do is we're going to approximate the area by chopping it up into some rectangles. So here what I've done is I've created 4 rectangles, 1, 2, 3, 4, and each rectangle has an equal width. Now this is going from 0 up to 2. So what we're going to do is we're going to partition that whole interval, 0 to 2, into 4 equal subintervals. So this is what it's called. It's called a partition, and we're going to partition that whole interval, 0 to 2, into 4 equal subintervals. Now to figure out how wide each one needs to be, we need to do a little bit of calculation. We're going to calculate something called delta x. Now it's going to be our little width of each of these little rectangles. So to calculate that delta x, we take the entire length of the interval, which in this case is 2 minus 0, okay, and we're going to chop it up in this particular example into 4 rectangles. So I want to chop this up into 4 equal pieces. So 2/4 is the same as a half, or 0.5, and that's why each one of these is a width of 0.5 going across. Now this is what the partition would look like. These are the subintervals. The first rectangle is going to go from 0 up to 0.5, and then the next one's going to go from 0.5 up to 1, and then the next one's going to pick up at 1 and go to 1.5, and then the last one's going to pick up at 1.5 and go to 2. So there is what we call our partition, and it's just this little subinterval here up to this one, then to this one, and then to this one. So we get 4 of them because we wanted 4 rectangles. Now what would be the area of these rectangles? Well, to calculate area, you need a length times a width, or a height times a width. I'm going to think of it as height instead of length. So we're going to do height times width. Now our width is exactly this distance right here. Each one of these has a width of that 0.5. So the width is going to be always your delta x, and in this problem that happened to be our 0.5. Now the heights of these vary. Notice this first rectangle goes up to a height of 4, and then that's how high my rectangle is. So this is a height of 4. The next one only goes up as high as however the function is at a half, and then it cuts across. And then the third rectangle goes up however high the function is at 1, which happens to be 3, and cuts across. And then the last rectangle goes up as high as 2, and then cuts across. So the first rectangle goes up as high as 0. The second rectangle goes up as high as the 0.5. The third rectangle uses the 1 to tell me how high to go. And the fourth rectangle uses the 1.5 to tell me how high to go. So we're going to use the left endpoints of these partition subintervals to figure out how high to make my rectangle. And that's just a conscious decision. You don't have to use the left endpoint. You could use the right endpoint, or you could use a different point as long as it's between your partition. I just find it easier sometimes to use that left endpoint, but we will do problems with other choices as well. So here's what our areas are going to look like. For rectangle number 1, we want to go as high as our function is when x is 0. So that would be f of 0. F of 0 is this height right here, which just so happens to be 4. And then we're going to multiply that height by the width. And the width, remember, is that delta x, which is 0.5. So 4 times 0.5, which is 2, is the area of this first rectangle. Now let's add to that rectangle number 2. So rectangle number 2 has as its height however high this is when I use an x value of 1/2, because that's this input value right here. So I'm going to use f of 0.5 for my height, and I would figure that out by plugging that into this function right here. So I would actually plug in 0.5 for x and figure out what that is. And when you plug it in, it's 3 3/4. And then we need to multiply that by our delta x again, our width. So 3 3/4 times 0.5. Okay? Then for rectangle number 3, now we're going to go as high as this point is when x is 1. And if you were to plug in 1, 4 minus 1 squared is 3. So that's exactly what we would have predicted. Okay? So we're going to use f of 1 times our delta x, which is 3 times 0.5. And then for our last rectangle, that one is supposed to have a height however high the function is when x is 1.5. So f of 1.5 times our delta x. And when you plug in 1.5 into this function, you get 1.75. And what we want to do to get this whole approximation is add together these 4 areas, these 4 rectangles. Now you can do that, a couple different ways. You can do 4 times 1/2 plus 3 3/4 times 1/2 plus 3 times 1/2 plus 1.75 times 1/2, or if you want, it'll give you the same answer if you add up all these heights first and then multiply that answer by 0.5. No matter how you do it, you're going to get 6.25. Okay? So there is our area approximation using these 4 rectangles. Now, do you think that would be a good approximation? Look at those 4 rectangles. Do they have as their areas something similar to the area of the actual curve underneath? Hopefully you can see no, because each of these rectangles is a little bit of an overestimate, and they actually get worse as you move down. We're going to be overestimating that area by all those little red shaded pieces. So this is probably too high, right? This is going to be too big of an approximation. So how could we make it better? What could we do to improve our approximation? Well, we can narrow our rectangles and make them be smaller so that we have more of them. So we could go here and here and here and here and so forth. So instead, this picture uses the same curve, but now it has 1, 2, 3, 4, 5, 6, 7, 8 rectangles. So we could use 8 rectangles instead. Now I'm not going to do all of the computation for you, but I do want to show you a couple of things that change. This delta x is now going to change. Our width of this whole interval is still from 0 to 2. So we want to take that interval 2 to 0, and this time we're chopping it into 8 equal pieces. So this time our rectangles are going to have a width of 1/4. So your partition would look like this. It would start at 0, and the first rectangle goes up to 1/4. Then the second rectangle picks up at 1/4 and goes to, 1/2. And then you would go from 1/2 to 3/4, and then 3/4 to 1, and so on until the very last one, which is going to be at 1 3/4 up to 2. And we're still going to use those left endpoints to determine all of these heights. I'm always using the left endpoint of that subinterval to tell me how high to go on my function. So your area would look like the height at that left endpoint. So f of 0 times the width, and the width here is always that 1/4, that delta x. So that would be the area of the first rectangle. Then the second rectangle would go as high as the function is at 1/4 times our width, plus the third rectangle would be however high the function is at 1/2 times our width, and all the way down to our very last rectangle, which uses 1 3/4 as our input times our width. And then you would punch each of those in to your calculator using the function 4 minus x squared. So you'd plug in 0, then you'd plug in 1/4, then you'd plug in 1/2, you'd plug in 1 3/4. It would be a really nice option to use the table feature on your calculator, where you can just type in your function 4 minus x squared into your y equals, set your table at 0, and set your change in table to be 1/4, and then it lists out what each of these values are all at once, so you don't have to recalculate each one. So you would just set your table to start at 0 and set your change in table to be this width of 1/4. And that way you're getting each of these function values listed out for you in your table automatically instead of having to punch each one in yourself. Okay? And when you do all that, you end up with 4.875. And that is definitely much smaller than what we had before, because we're decreasing that error by shrinking the number of our rectangles. So would this be an underestimate or an overestimate of the actual area? You can see from the picture that even when we use 8, we still get all of these little rectangles being slightly higher than the actual curve itself. So this is going to be an overestimate since all the rectangles lie above the curve. Okay? All right. Let's approximate the area again, and let's see how we're doing it slightly differently here. So I'm going to use 4 rectangles again. But look at what's different about them. This very first one, I'm not going as high as 0. Here I'm actually going as high as 0.5. So I'm using the right endpoint and moving over left horizontally to tell me how high to go. And on the second rectangle, I'm using the right endpoint 1, moving over horizontally to the left to tell me how high that rectangle should go. The third rectangle, I'm using the 1.5, plugging that in and going horizontally across to tell me how high to go. And this one, you can't even see it because when I go across to that right endpoint, which is at 2, that height is actually 0. So this last rectangle actually has no area at all because its height is 0. So here's what's different. We're still using 4 rectangles. So our delta x is still going to be 2 minus 0 divided by 4, which makes each one have a width of 1/2. And that means my partition is still going to be 0 to 1/2, 1/2 to 1, 1 to 1.5, and then 1.5 to 2. But what's different is this time I'm going to use right endpoints to get the height. So when I plug into my function, the x's that I should plug into my function are the 1/2, the 1, the 1.5, and the 2. So my area is going to be the function at 1/2 times that width, plus the function at 1 times the width, plus the function at 1.5 times the width plus the function at 2 times the width. So when I plug in a half into my function 4 minus x squared, that turns out to be 3.75. And I'm multiplying that by my width, which is my 1/2. When I plug in 1, I get 3 times my width. When I plug in 1.5, I get 1.75 times my half. And when I plug in 2, 2 squared is 4, 4 minus 4 is 0. So that's why this last rectangle doesn't go at all anywhere. It's flat. And when you multiply these all together and add them up, you get 4.25. So this approximation is even lower. Now it's 4.25. Now, based on the picture that we see here, would this be an underestimate or an overestimate of the actual area under the curve? Well, this time, each of our rectangles is leaving a significant gap right here, 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 and then all of this. So we're leaving out all those blue pieces of area in our calculation. So this time, this is going to be an underestimate because all the rectangles lie below the curve. So we want a kind of happy medium. We want to have a little bit above, a little bit below if possible, so that we can try and get a more accurate approximation. So let's generalize this whole process that we just talked about. So to approximate the area under or bounded by a function f of x, the x-axis, and the vertical lines x equals a and x equals b, we're going to begin by partitioning the interval into n subintervals. So what we're going to do is we're basically trying to find the area under our function from a to b, and we're going to chop it up into n little subintervals. So to figure out the width of each one, we're going to make them equal widths. Then we just take the total length of that interval, and we're going from a to b, so that would be b minus a, however wide that is, and we're going to divide that by n, however many subintervals we're looking for. Then the partition is going to start at a and go up to a plus 1 width. Then it's going to pick up at a plus 1 width up to a plus 2 widths, then a plus 2 widths up to a plus 3 widths, and so forth. Now f of little m sub I is going to be the minimum value of the function on the I subinterval. So whichever point on that interval gives you the least height at all. That's what this is. So whatever the minimum y value is on that particular subinterval. F of capital M sub I is going to be whatever the maximum value of the function is on that I subinterval. So in our last couple of examples with that 4 minus x squared, the left endpoint gave us the maximum and the right endpoint gave us the minimum. Okay, but that could vary depending on your particular function, whether it's the left or the right or maybe even something in between. So if we draw a picture of this, I'm just going to make up a graph here, and I'm going to make or take a look at just one particular subinterval, one particular rectangle, if you will. On this particular graph, you can see that on this particular section of the function, the highest value happens to correspond to that left endpoint. And again, that's just because of the shape of this particular function. That may not always be the case that you have the maximum at the left. But if I draw this over and across, then this is f of big M sub I. And then if you look at that same little section of the graph, the right endpoint corresponds to the lowest y value. So that would be f of little m sub I. And that would be this little red rectangle right here. So we call that little red one the inscribed rectangle, and it lies inside of the true area. We call the black one the circumscribed rectangle, and it lies outside of the true area. So you can kind of see from the picture that the area of the inside or inscribed rectangle, the f of m sub I times delta x, that area has to be less than or equal to the area of the circumscribed rectangle, the black one. Okay, so this is really saying the red area is less than or equal to the black one. Okay, so that should hopefully make sense from the picture. And what we can conclude from that is we're going to call the lower sum, so little s sub n, the sum of all of these inscribed rectangles. And we're going to call the upper sum, capital S sub n, the area of all these circumscribed rectangles. So the lower sum are all the rectangles that are slightly lower than the curve, and the upper sum are going to be all the rectangles that are slightly above the curve. And what we can see is that the true area must be somewhere in between, right? The actual area of the region has to lie between these two sums. So the area underneath the curve is maybe bigger than the lower sum but smaller than the upper sum. Okay? So let's find this lower and upper sum on the interval 0 to 2 for the function x squared. Okay, so let's draw what this is going to look like. X squared is just a nice parabola, and we're going from 0 to 2. So we're trying to find this area, and we want to find the lower and the upper sum. Now, on this particular problem, it doesn't tell me how many rectangles to use. In fact, these are in terms of n. So we're going to use n rectangles. So we're keeping it very general. So first let's find that delta x, the width of each one. So what we do is we take this whole interval, which would be 2 minus 0 in length, and we're going to chop it into n rectangles. So this means each rectangle is going to have a width of 2 over n. So my partition would look kind of like this. It's going to start at 0, this leftmost endpoint, and the very first rectangle is going to go over one width of 2 over n. So that would be this one. Then the next rectangle is going to pick up at 2 over n, and it needs to go over a width of 2 over n as well. So 2 over n plus another 2 over n means it's going to stop at 4 over n. And then the next one, if it went over another 2 over n, it would stop at 6 over n. So the third rectangle picks up at 4 over n and goes to 6 over n, and so on until we get up to 2. Okay? So we're going to have n of these. So let's figure out what our circumscribed and inscribed rectangle heights are going to need to be. So if we look at the shape of this graph, should I use left endpoints, right endpoints, or something else to figure out the lower sum, those inscribed rectangles? Let me draw in a few more here so it's easier to see. If you look in the middle here, if you look at this particular rectangle right here in blue, we want for the lower sum the minimum value on that little piece of the graph. And the lower point, the lowest point on that little section is the left endpoint. And if I use that going across, I'm going to get that what we call inscribed rectangle. So for the lower sums, we need to use the left endpoint. So that is going to look like this. So little s sub n is going to be the first rectangle using its left endpoint, which would be this 0, times its width, which is that 2 over n. Then the second rectangle is going to use its left endpoint, 2 over n, times its width. Then the third rectangle uses its left endpoint, 4 over n, times its width all the way up to this very last one, which I didn't even write down, times 2 over n. So to find the area using these lower sums, we want to be using that formula that said that the lower sum is going to be the sum from I going from 1 to n of f of those little m sub i's times delta x. So those little m sub i's are these right here. And what I want to try to do is find a formula for this m sub I so that I generate each of these left endpoints correctly. And I want to do it so that I can write this in this summation notation. So let's think about how I can come up with a formula for this little m sub I so that I'm getting each of these left endpoints every time. So it's kind of like we did at the beginning of this lecture, trying to look at this sum and come up with a formula for what it would be in summation notation. So this very first left endpoint is 0. And what I want to do each time is add some of these widths to it. And these widths are 2 over n. Now, do I want to add, or how many of those widths do I want to add so that I generate the correct one for the rectangle that I'm looking at? Now, the left endpoints I actually think are harder to come up with this formula than the right endpoints, and we'll see that in a moment. But think about this for a minute. For the first rectangle, which was this one right here, we wanted to end up with an input of 0. So I don't want any of these 2 over n's to be used. I want to just start at that 0. For the first rectangle, I wanted 0. For the second rectangle, I wanted exactly 1 of these 2 over n's. So if I is 1, representing that first rectangle, I can't put just an I right here, because if I was 1, then I'd be adding 2 over n. So what we have to do is shift it slightly and change this to I minus 1. And let me show you why this works. If I is 1, then this becomes 1 minus 1, which is 0, and we just get 0. If I is 2, representing this second rectangle, then we do 2 minus 1, which is 1, times 2 over n, and we get exactly that 2 over n that we're looking for. If I is 3, 3 minus 1 is 2, 2 times 2 over n is 4 over n. So we're getting this input that we want for that third rectangle. So it's slightly complicated here because we have to actually shift that I by a minus 1 so that we're getting that left endpoint instead. So here's what this summation notation looks like. The sum from 1 to n of our function evaluated at this formula, and I'm going to drop that 0 and just write this as 2 over n times I minus 1. And then our delta x were all of these 2 over n's. So this is what the lower sum looks like. Now we're going to come back and actually figure out what this is, but before we do that, let's go ahead and compare this lower sum to what the upper sum is going to look like. So let's look at our picture over here and look at that same little section of the graph. What would the upper rectangle or the circumscribed rectangle have to look like? Well, it would use the right endpoint and come across like this and lie outside of your function. And that's the right endpoint that we're using to generate that taller rectangle. So for the upper sum, we actually want to use these right endpoints each time. So for the upper sum, I'm going to come down here just a little ways. We're going to use right endpoints. And that means this capital S of n is going to be f of, for the first right endpoint, that's 2 over n, times the width, plus for the second rectangle, now we're going to use 4 over n, and then we're going to use 6 over n, and so on, all the way until we use 2. So this will be f of 4 over n times 2 over n plus f of 6 over n times 2 over n, all the way up until that last rectangle where we use the right endpoint 2 times our width of 2 over n. So let's see if we can come up with a formula for this capital M sub I, which is going to generate each of these right endpoints. Now the formula is very similar to the formula we had for the left endpoints. You're always going to start at your initial left endpoint, which in this problem is 0. And then to get that first right endpoint, we want to go over 2 over n. And then we want, for the second endpoint, we want to go over 2 over n's. For the third rectangle, we need to go over 3 2 over n's. For the fourth rectangle, we need to go over 4 2 over n's. So if I is 1, we'll get 2 over n. If I is 2, we'll get 4 over n. If I is 3, we'll get 6 over n. And if I is n times 2 over n, the n's cancel, giving us just 2. So you'll see that this formula for the right endpoint is very similar to the one for the left endpoint, but it's actually a tiny bit simpler because you don't have to shift that I. Okay? So that's typically how they work out. The right endpoint, you use just the I. For the left endpoint, you use the I minus 1 times that width. Okay, so this is what our capital S sub n will look like. The sum from 1 to n of f of capital M sub I delta x. So in our formula, that's going to be f of 2I over n times 2 over n. Our width was the 2 over n, and our capital M was this 2I over n that we got right here. Okay? So here's our formula. Now what we want to do is actually figure out what this becomes. Now for time's sake, I'm only going to do one of these just to kind of show you the process, but you can do exactly the same method on both of these. So you can do it on this one or this one. You should be able to do it for both, but I'm just going to show you this one down here at the bottom. Now what I'm going to do here is use that same process that we did on an earlier problem. We're going to actually come up with a formula for what this is. We're going to get rid of that summation notation and come up with a formula for what this is just in terms of n. Now remember that our function is the x squared function. So in order to progress from here, to move on to the next step, I'm actually going to take this 2I over n and I'm going to plug it into my function. So this upper sum would become the sum from 1 to n of 2I over n plugged in to our function x squared. So it becomes 2I over n quantity squared times that width. So these are your heights and these are your widths. When you multiply those together, you get areas, and we're adding each of those rectangular areas together, and that's what this summation notation does for us. So let's simplify this. 2I over n quantity squared becomes 4I squared over n squared times 2 over n. And just multiplying some like terms there, 2 times 4 is 8, n squared times n is n cubed. And I can pull that 8 over n cubed out front because it doesn't have an I in it. I'm just leaving the I squared where it is. Now that is one of those summation formulas that we talked about earlier today, the big complicated one. N times n plus 1 times 2n plus 1 all over 6, the sum of the squares. So that is going to become 8 over n cubed times, and then this whole sum now gets replaced with this formula, and now there's no more summation symbol in there anymore because I've just figured out what that sum is. It's this formula right here. Now I'm not going to do a whole lot of simplifying. I might cross off one of these n's, but this is going to become an 8 times n plus 1 times 2n plus 1 all over 6n squared. So this is the formula for the upper sum. Okay? Now doing a very similar process, you could get the formula for the lower sum. I don't have enough room to really do that on here, so I'm going to leave that part off. But what we could then do, once we get this upper and this lower sum, is what we can do is take the limit of that. Remember what happens when you take the limit as n goes to infinity? Let's take a look at what this limit would turn out to be. Think about what would dominate on the top. I'm not even going to bother to FOIL everything out on the top. Just tell me what the dominant term would be. It would be this 8 times that n times that 2n. And 8 times n times 2n is going to be 16n squared. And on the bottom we have n squared. The n squareds cancel out, and 16 over 6 reduces to 8/3. So in the limit, this goes to 8/3. Now what does that tell me? From our picture over here, what it tells me is that the lower sum and the upper sum are not going to give you the exact area. You can see from the picture that the upper sum is going to be an overestimate and the lower sum is going to be an upper estimate. But if you were to take more and more rectangles and make the number n go to infinity, that's what we did when we took our limit, then these upper and lower sums would start to approximate each other and get closer and closer together. And what you would get is in the limit, that sum becomes the exact area. So this 8/3 is the exact area under x squared from 0 to 2. So the upper and lower sums won't give me that exactly until I take the limit as n goes to infinity. And that's what this theorem says on the very next page. Okay? So, our theorem, let f be continuous and non-negative on the interval a to b. The limits as n goes to infinity of both the lower and upper sums exist and are equal to each other. That is, that the limit as n goes to infinity of the lower sum, which are all these f of little m sub i's, equals the limit as n goes to infinity of the f of capital M sub i's, which turns into the limit of our upper sum. These delta x's are those b minus a over n's. F of m sub I and f of capital M sub I are the min and max values of the function on the subinterval. So what this theorem is saying is that as you go to infinity, the limit of the lower and the upper sum become the same thing. And that, in fact, is going to become our actual true area. So the significance of this is that when you take the limit as n goes to infinity, this will turn into your true area. And what this theorem tells us is that since the lower and the upper sums are going to equal each other in that limit, it doesn't matter which endpoint you use. So you can use either the left endpoint or the right endpoint or something else entirely. And in the limit, it will give you the true area, and it doesn't matter which method you use, just use whatever's easiest for you. So you can use either the lefts, the rights, the midpoints, something else entirely, and in the limit, they all become equal. And not only do they become equal, they become the exact area. Okay, so definition, the area under your curve is going to be the limit as n goes to infinity of the sum from 1 to n of f of c sub I delta x, and this c sub I can be any endpoint in between your subinterval points. So you can use your c sub i's to be left endpoints or rights or midpoints or whatever is easiest for you. And we're going to let our rectangles have equal width b minus a over n each time, again, just to make our life easier. So you get to choose what endpoint you want, and when you take the limit of that as n goes to infinity, it's all going to work out in the end and give you that exact area. So let's use or find the area of the region bounded by 2x minus x cubed on the interval 0 to 1. Use the limit definition of area. That's what this is right here. This is called the limit definition of area. So what you have to do is you have to chop up your function into n rectangles, and then you take the limit of that area as n goes to infinity. So they're not telling us a specific number of rectangles to use here. We get to use just a general n. So we're going to use n rectangles, and we're going to make them all equal just to make our life easy. On this particular problem, we're going from 0 to 1, so the width of that interval would be 1 minus 0, and we're chopping it up into n equal pieces. So that means each rectangle is going to have a width of 1 over n. So the partition is going to start at 0 and then go to 1 over n, then pick up at 1 over n and go to 2 over n, then pick up at 2 over n and go to 3 over n, and so on, all the way until they stop at 1. Now what I like to do is choose the endpoint that's going to make my life easy. And usually, I always find to make life easy, that means use right endpoints, because they have a simpler formula to generate. So the right endpoint, you can see that that's going to be 1 over n, 2 over n, 3 over n, all the way up to 1. Here's the formula that will generate that. You always start with your initial left endpoint 0, and from there you're going to be adding the appropriate number of widths depending on which rectangle you're looking for. So if I want the first rectangle, I want to go over a width of 1 over n to get to this first right endpoint. For the second rectangle, I want to go over 2 1 over n's, which is why I got 2 over n here. For the third rectangle, I want to go over 3 1 over n's, which is why I got 3 over n. So here's the formula. Our width is 1 over n, and I want to go over I of them for each rectangle. So when I is 1, I'll get this. When I is 2, I'll get this. When I is 3, I'll get this, and so forth. So your right endpoint formula will be whatever this leftmost starting point is. Most of the time it's 0, but not always, plus I times whatever your width is. Okay? Once you know that, and I'm just going to simplify this to I over n, now we can write out what our sum is going to be for our area. So the true area, the exact area, will be the limit as n goes to infinity of the sum from 1 to n of f of these right endpoints times my delta x. And I know what my delta x is, so let's substitute that in. So my delta x is 1 over n. Okay? So here's my initial formula. We haven't used our function at all yet. So now what we're going to do is we're physically going to plug in I over n into this function. So we need to find f of I over n. So that's going to be 2 times I over n minus I over n cubed. And that is all going to go right here. This is going to be one of those long, messy problems where you're going to have a lot of simplifying to do, and it's going to take a lot of paper. All of these limit definition of the area problems are always going to be long and messy. Okay? Now, to help clean this up, ignore the limit for now. You're not going to do that part of the problem until the very, very, very last step. So ignore that. I'm still going to write it each time, but we're not doing it yet. The first thing I'm going to do is this width is a constant width. It's not a function of I. So you can always pull that width out front of your sum. get it out of the way. Now let's go ahead and simplify this function here. I'm just going to multiply this and make it 2I over n, and I'm going to go ahead and cube I cubed over n cubed. Now what I'm going to do, I'm going to recopy my limit, I'm going to recopy my 1 over n, I'm going to recopy my sum, but now I'm going to break this up and make it into two sums, 2I over n minus the sum of I cubed over n cubed. Okay? Notice that I have that 1 over n times both of those because I pulled it out front of both. Be careful with your brackets there. So that 1 over n is going to stay way out front. And now with this first sum, I'm trying to get it so I just have an I there. So I'm going to take this 2 over n and I'm going to pull it out front. So this becomes the sum of just I. And we have a formula for that. Then for this one, I'm going to take this n cubed and I'm going to pull it out as well, but it's in the bottom, so you need to pull it out as a 1 over n cubed. So that leaves me with an I cubed, and I have a formula for that. So I have a formula for this. The sum of I is just n times n plus 1 over 2. And I have a formula for this. The sum of I cubed is just n squared times n plus 1 squared over 4. That was one of those that we talked about at the very beginning of this lecture. So let's substitute in this formula right here and this formula right here. So recopy all the stuff out front. Don't forget your 2 over n out front, and then in parentheses I'm going to write that n times n plus 1 over 2. Don't forget your 1 over n cubed. In parentheses, I'm going to write n squared over n plus 1 squared all over 4. Okay, now there's, it's kind of up to you how much simplifying you want to do here. I'm going to try to get away with as little simplifying as possible. In this first part, I'm going to cancel out my 2's, I'm going to cancel out my n's, so this is just n plus 1. Over here, I'm going to cancel out 2 of these n's, so I'll have a 4n left, and I'll have n plus 1 squared on top. Now I'm going to go ahead and distribute this 1 over n across. So I'll have 1 over n times n, which is 1, plus 1 over n times 1 stays 1 over n, minus, when I multiply this 1 over n across, it's going to join that bottom and become 4n squared in the bottom and an n plus 1 squared on top. That's as far as I'm going to go in terms of simplifying, because now I'm ready to take a limit. N is getting really, really big. The limit of a constant is a constant, so this 1 stays 1. But as n gets big, 1 over infinity goes to 0, so this term will go to 0. And then this one is acting like an n squared on top, that's the dominant term, and a 4n squared on the bottom. So the n squareds are going to cancel, giving me just a 1/4, but there's a minus in front. So 1 minus a 4th means this is 3/4. So that is the area under y equals 2x minus x cubed over the interval 0 to 1. That's the exact area. Okay? All right, we're going to try it again. Okay? Find the area of the region bounded by y equals x squared on the interval -2 to 0 using the limit definition of area. So step 1, find your delta x. Okay? We're using n rectangles here. So we're going to take this interval, do the right endpoint minus the left endpoint to get its width. So 0 minus -2 divided by n. So the width is going to be 2 over n. That means my partition, notice this one doesn't start at 0. This one starts at -2. So the next endpoint over is going to be -2 plus that single width. So we want to go over one width to close off that first rectangle. then that rectangle, or the next one, will pick up where that one left off, and I want to add to that another 2 over n, which is going to make it negative 2 plus 4 over n. So I've added 2 of these widths to get that second right endpoint. If you wanted to continue writing these, this one would pick up at negative 2 plus 4 over n, and then I would add another width to that. 4 over n plus another 2 over n would put me at negative 2 plus 6 over n. And then this would continue until I get to 0. So what we want to do to make your life easier is use the right endpoints. So that would be this, 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 all the way up to there. So we need a formula that will generalize those using I. Notice that they all start with a negative 2. That was this leftmost endpoint. And then to get the 2 over n's here, this one is when I is 1, because we're just going over one rectangle. This would be when I is 2, this would be when I is 3, and this is going to be when I is n. So how could we generate a formula for that? Well, each width is 2 over n. And I want to multiply by however many rectangles I am looking at. So for I being 1, I want to go over 1 2 over n. When I is 2, I wanted to go over 2 I over n's. When I was 3, I wanted to go over 3 I over n's. So each of these this formula generates each of these right endpoints as I varies from 1 all the way up to n. When I is n, the n's cancel, and negative 2 plus 2 will give me that 0. So I am getting each of these right endpoints when I use this particular formula. And the rule of thumb here is that it's always going to be whatever this left endpoint is, I'll call that A, plus I times whatever your width is. That's kind of the general formula that will generate that right endpoint every time. Whatever that left endpoint is, A, plus I times your width. Okay? So now that we know our endpoints and we know our widths, we're ready to write our area. So here's the limit definition of area. The true area, the exact area, will be the limit as n goes to infinity of the sum from 1 to n of f at this right endpoint times the width, which we know is 2 over n. So this is your height, f at that endpoint, times your width. So we're doing lengths times widths to get areas. And we're just adding up all of those rectangular areas, and then we're taking the limit of that as n goes to infinity to make them become more accurate. Okay? So next thing that we do, now that we have our formula, is we need to use our function. So this is your f of x. F of x is x squared. So I need to take all of this. This is now going to become my input into that function. I need to substitute in that right endpoint into that squaring function. So this is what it would turn into. We've got our limit, we've got our sum, and now f of this stuff becomes this stuff squared, because this is a squaring function. So all I did was put it in for x, wrap it in parentheses, and square it. Okay? So now what I'm going to do is I'm going to just do algebra. All right? The first thing I'm going to do is I'm going to take this width. You can always, always, always pull that width out front of your sum right off the bat, because it will not have an I in it. Next thing I'm going to do is I'm actually going to FOIL out this function so that I can work with it. So this is going to be the limit as n goes to infinity of 2 over n times our sum. And when I square this out, negative 2 squared is 4. In the middle, I'll get a negative 2 times a 2i over n, which is a minus 4i over n, but I'll get 2 of those, one for the inners, one for the outers. So we're going to get a minus 8i over n, plus this 2i over n squared. So 4i squared over n squared. So all I did there was I FOILed that out. Okay? Now what I'm going to do is I'm going to break up each of these three pieces into three different sums. Leave this 2 over n out front and use brackets, and I'm just going to take the sum of the 4 minus the sum of the 8i over n plus the sum of the 4i squared over n squared. And then what I'm going to do is I'm going to pull out front of those individual sums any constants like 4's and n's that don't need to be there. So the sum of 4, that's actually just the sum of a constant. So I'm going to leave that 4 where it is. But this 8 over n, I'm going to pull that out. So this just becomes the sum of I. And then this 4 over n squared, I'm going to pull that out. So this becomes the sum of I squared. And now we have a formula for this guy, and this guy. So the sum of a constant is a constant times n. The sum of I is n times n plus 1 over 2. And the sum of I squared is n times n plus 1 times 2n plus 1 all over 6. So we're just going to substitute those in. So the sum of a constant times n, here my constant is 4, so this will be 4 times n, minus 8 over n times the sum of I is n times n plus 1 over 2, plus the sum of I squared is n times n plus 1 times 2n plus 1 all over 6. Now you should no longer have any more summation symbols because we've used the appropriate formula to get rid of them. All right, let's simplify a little bit on the inside first, and then we'll distribute this 2n across. So I can divide into that 8, and I can cancel out some n. So I'm going to have a minus 4 times n plus 1. Here I'm going to cancel out some 2's, so I'll get a 2. And I'm going to cancel out one of these n's, so I'll have a 2n plus 1, 2n plus 1, all over a 3n on the bottom. Now let's distribute this 2 over n across. 2 over n times 4n, the n's cancel, giving me 8, minus 2 over n minus 4 times n plus 1. I'm just going to do 2 times 4 and make this an 8. I'll leave that n plus 1 in parentheses, and I'll leave that n in the bottom. Plus 2 times 2 is 4 times all this other stuff that's on top. And n times 3n is 3n squared. All right? Now I'm ready to do my limit. You can simplify more if you want to, but I'm just going to jump right into my limit. This becomes just 8 because the limit of 8 stays 8. This acts like an 8n on top over an n. The n's cancel, so I'm just going to get a minus 8. And then this one acts like a 4 times an n times a 2n, which is an 8n squared. And on the bottom, we have a 3n squared, and the n squareds are going to cancel out. So as n gets really big, this is just going to become 8/3. These cancel, so my limit is 8/3. Okay? Big, long, tedious problem. All right, last one. This time we're going to go back to approximations. We're not going to find an exact area, so we don't have to do that whole limit of a sum thing. But what we do want to do here is approximate the area of the region bounded by the curve y equals x squared plus 4x on the interval 0 to 4 using midpoints and 4 subintervals. So I just wanted to show you a problem where we're not using left or right endpoints. On this particular one, we're going to use midpoints. So first of all, let's just get a sketch of the graph so we can kind of visualize what's going on. X squared plus 4x is just a parabola. It has zeros at 0 and well, at 0. Let's just start with that. And then this is going to arc up like this, and at 4 we're going to be somewhere over here. Okay, so this is what we're looking like, and we're going to use 4 subintervals. So we're just going to chop this up into 4 nice rectangles. Now what you would normally do right off the bat, we're going to find that delta x. So we take our interval and you do the right endpoint minus the left endpoint, and you divide it or chop it into however many subintervals you want. We wanted 4. So that just means that the width of each of our rectangles is going to be 1, which we could probably already see from over here. Now the partition then is really a nice one. You're going to start at 0 and go to 1, then you're going to pick up at 1 and go to 2, then 2 to 3, and then 3 to 4. Now here's what's different. Instead of using a right or a left endpoint, we're going to actually use midpoints on each subinterval. So what would be the midpoint on the interval 0 to 1? What's the midpoint between 0 and 1? 0.5. What's the midpoint between 1 and 2? 1.5. What's the midpoint between 2 and 3? 2.5. And what's the midpoint between 3 and 4? 3.5. So to get our approximate, this isn't the exact, it's just an approximate because we're not doing a limit. To get the approximate area, we're going to take our function at a height of 0.5 times our width, which is 1. So this first rectangle is only going as high as that halfway point, and it would look something like that. And then the next one is only going to go as high as 1.5, and it would look like that. And then halfway, like that, and about halfway, like that. So some people think that the midpoint approximation is actually better because you can see that you're sort of overestimating here, but you're also underestimating here. So they kind of balance each other out, probably giving you a more exact answer or approximation than if you had done strictly a left or a right endpoint. So that's why people sometimes use midpoint rules instead of left or rights. So let's finish what we have here. This would be the area of that very first rectangle. The second rectangle would go as high as the function is at f of 1.5, and then we would multiply by our width of 1. The third rectangle goes as high as 2.5 times our width of 1, and the fourth rectangle goes as high as 3.5 times our width of 1. And then you use this function, so you'd have to plug in 0.5 squared plus 4 times 0.5 to get this value, and that's 2.25. And then you would plug in 1.5 for x, which would be 8.25. And then you'd plug in 2.5, which is 16.25, and then you'd plug in 3.5, which is 26.25. Again, using a table on your calculator can make that calculation easy. You would just type this into your y equals, and then you would start your table at 0.5, and then you could go up by 1 to generate each of these other midpoints. When I add all 4 of these together, we get 53. And as I mentioned before, because we're sort of overestimating on the left but underestimating on the right, this is probably going to be a much better approximation than if I had used 4 rectangles and done them with a left endpoint, or 4 rectangles with the right endpoint. So this is going to be a lot more accurate because of the shape of this particular graph. All right, this is a tough one. Those limits, definitions of the areas are long, tedious, and easy to make mistakes on. So be really, really careful and have some patience. Good luck. That ends our lecture on summation notation and area.